Hello dear students, you are welcome to Har Ghar Pathshala. Myself Rajesh Nanda, lecturer physics, presently posted at Government Model Senior Secondary School, Kotli, District Mandi. Before I start today's topic of nuclear physics, here is an important message for you. To protect yourself from any kind of infection like the COVID-19, wash your hand with the soap regularly, wear mask properly, avoid to touch your eyes, nose, mouth with your hand, keep the physical distancing at the place of the crowded area, and the important one, follow the instruction provided by the government time to time. In the nuclear physics today, we will discuss the nuclear fusion, energy generation in the star, and the controlled thermonuclear fusion. We start with the nuclear fusion. We learned earlier that binding energy per nucleon is minimum in the middle range of atomic number. Hence, energy can be produced by breaking the heavy nuclei into the smaller fragment as well as by fusing the light nuclei to become a bigger nucleus. In both cases, binding energy per nucleon increases and different amount of energy is released in the process. The process by which nuclear reaction between the light element form the heavier element up to the iron. In case where interacting nuclei belong to the element with the low atomic number, for example the hydrogen atomic number is 1, and for its isotope, hydrogen like isotope, that deuterium and tritium, substantial amount of energy is released. The vast energy potential of nuclear fusion was first exploited in the thermonuclear weapon or in the hydrogen bomb, which were developed in the decade immediately following the World War II. Meanwhile, the potential peaceful application of nuclear fusion, especially in view of the essential limitless supply of the fusion fuel on the earth, it has encouraged to in an immense effort to harness this process for production of the power. In the nuclear fusion, what is nuclear fusion? That is defined as a type of nuclear reaction in which two light nuclei merges into one another to form the heavier nucleus, accompanied by the release of a large amount of energy. When two light nuclei are brought close to each other within the range of nuclear forces, attractive nuclear forces may combine them to form the bigger nucleus, and in this process energy is released due to the mass defect, and this process that is called the fusion process. For example, two deuteron heavy hydrogen can fuse together, 1H2 plus 1H2, and they form the tritium according to this equation. 1H2 plus 1H2 give the 1H3 plus 1H1 plus amount of energy 4 MeV, and then this 1H3 again combined with the 1H2, they form the helium 2He4 and neutron with the release of energy amount 17.6 MeV. Adding these two equations, we will get the 1H2 plus 1H2 plus 1H2. They form the helium 2He4 plus neutron plus proton with the release of the total energy of 21.6 MeV. This equation indicates that when three deuteron are fused together, then this alpha particle 2He4 and a neutron 0 and 1 and a proton 1H1 are formed with release of energy 21.6 MeV. Energy produced per deuteron fuses that come out to be equal to 21.6 or equal to 7.2 MeV. 21.6 by 3, then that amount will be equal to 7.2 MeV. Then the fusion of 3 deuteron to form the alpha particle, 1H2 plus 1H2, they form the 2He3 with the end of neutron 0 and 1 and with the release of energy 3.3 MeV. And then this 2H3 again combined with the 1H2, they form the 2He4 alpha particle and the proton with the release of energy 18.3 MeV. Adding these two equations, we will get 1H2 plus 1H2 plus 1H2 means 3 deuteron are fused, they form the 2He4 alpha particle. On the other hand, and released with 0 and 1 neutron and alpha proton 1H1 with the total amount of energy released, that is 21.6 MeV. On the other hand, we see that in the fission process of uranium-235 nuclei, energy generated is 200 MeV. So it might seem that fusion is weaker, but its effect is reverse. Just compare the number of atom of the deuteron and uranium in 1 gram of corresponding sample. Number of atom of the deuteron is much higher than the number of atom of uranium in 1 gram sample. Hence, same mass of substance, total energy released in the fusion, that is much larger than the fission process. This process of fusion of light nuclei to form the bigger nucleus is favorable from the perspective of energy, but bringing the nucleus so close distance is however very difficult task. Range of nuclear forces, that is of order of the fermatometer 10 raising power of minus 15 meter. On the other hand, radius of atom is of order of 10 raising power minus 10 meter. We can see that size of the atom is much bigger. So, when two atoms are brought closer, electron interact first. Repulsion between the electron make it difficult to approach to the nucleus. However, if there is no electron, even the nuclei carry the entire positive charge, hence will repel each other strongly at such small separation. Okay. Technique to start the fusion is to heat the gas to extremely high temperature. Okay, then we come to the energy released in the fusion reaction. Energy is released in the nuclear reaction if the total mass of resultant particle, that is less than the mass of initial reactant. It illustrates the suppose that two nuclei labeled as a X and A react to form the two other nuclei Y and A. X and A react to form the Y and A. The particle A and B are often the nucleons, either the proton or neutron, but in general can be nuclei, assuming that none of the particle is extremely internally excited. Each is in the ground state. Energy quantity Q value for this reaction is given as the Q, that will be equal to mass of X particle plus mass of A particle, that minus mass of the B and mass of the Y into the C square, mc square, where the m labeled refer to the mass of each particle and c is speed of the light. When the energy value Q is positive, reaction is exoric. When the Q is negative, reaction is endoric. Absorb the energy. When both the total proton and total neutron number are preserved before and after reaction, as in the DT reaction, then the Q value can be expressed in terms of the binding energy of each particle. Q will be equal to binding energy of Y plus binding energy of B particle minus binding energy of X minus binding energy of A. Then there are the two type of the fusion reaction. Fusion reaction are basically two types. One is that those that preserve the number of proton and neutron, and second is those that involve the conversion between the proton and neutron. Reaction of first type are most important for the practical fusion energy production, whereas those for the second type are crucial to the initiation of star burning. Our arbitrary element is indicated by the notation ZXA, where Z is charge of the nucleus, A is atomic weight. An important fusion reaction, the practical energy generation is that between the deuterium and tritium, the DT fusion reaction. It produces helium and neutron, can be written as D deuterium plus tritium give the helium plus a neutron. Here the left of the arrow before the reaction, there are 2 proton and 3 neutron. Same is true for the right. On the other hand, that which initiate the star burning involve the fusion of 2 hydrogen nuclei to form the deuterium, HH fusion reaction. HH give the D plus beta particle plus a neutrino. B positive is positron and nu stand for the neutrino. Before reaction, there are two hydrogen nuclei, 2 proton. Afterward, there are 1 proton and 1 neutron bound together as a nucleus of deuterium, plus the positron and neutrino produces as a consequences of conversion of 1 proton to the neutron. Both of the fusion reaction are exotic and so called the energy yield. German born physicist Hans Bethe proposed in 1930 that HS reaction could occur when a net release of energy is provided. Along with the subsequent reaction, the fundamental energy source sustaining the star. However, practical energy generation require the DT reaction for the two reasons that first, the rate of reaction between the deuterium and tritium is much higher than that between the proton, and the second is net energy released between the DT reaction is 40 times greater than that of HH reaction. Then fusion reaction for the controlled power generation. The reaction between the deuterium and tritium are most important fusion reaction for controlled power generation, because the cross section for the occurrence of high particle plasma temperature required for the net energy release are moderate, and energy yield for the reaction are very high, 17.58 MeV. For the basic DT fusion reaction, it should be noted that any plasma containing the deuterium automatically produces some tritium and helium-3 from the reaction of the deuterium with other deuterium ion. Other fusion reaction involving the element with the atomic number that above the 2 can be used, but only with much greater difficulty. This is because the Coulomb barrier increases with increasing the charge on the nuclei, leading to the requirement that plasma temperature exceed the 10000000000 Kelvin if the significant rate is to be achieved. Very difficult. Fusion reaction for the control generation, some more of the more interesting reaction is H plus boron combine to form the 3 helium alpha particle with the release of the 8.68 MeV of energy. Second reaction is hydrogen plus lithium, they give the He3 and He4 with the release of the 4.02 MeV energy. Third reaction is He3 plus lithium give the proton plus 2 of the alpha particle with the release of the 16.88 MeV of energy. And fourth reaction, that is a 3 helium with the 6 lithium give the deuterium plus 7 beryllium with the release of energy 0.113 MeV. The reaction 2 convert the lithium 6 to the helium 3, ordinary helium. Interestingly, if the reaction 2 is followed by reaction 3, then the proton will again be produced available for the reaction of 2, thereby propagating this process. Unfortunately, it appears that the reaction 4 is 10 times more likely to occur than the reaction number 3. Then a hydrogen bomb or thermonuclear bomb. Thermonuclear bomb, also called the hydrogen bomb or the H bomb, weapon whose enormous explosive power result from the uncontrolled self-sustaining chain reaction, in which isotope of the hydrogen combine under extremely high temperature to form the helium. In this process, nuclear fusion, the high temperature that are required to form the reaction are produced by the detonation of the atomic bomb. Hydrogen bomb is a nuclear fusion bomb and it is also known as a thermonuclear bomb. Fusion of the heavy nuclei is used to make the bomb. We know that extreme temperature and pressure condition are required for the fusion. So, atom bomb or the fusion bomb is used at the igniter for the fusion bomb. Fission bomb are used as a igniter for the fusion bomb. Hydrogen nuclei that combine to form the heavy helium nuclei must lose a small portion of their mass, about 0.63%, in order to fit together a single atom. They lose the mass by converting completely into the energy, according to the Albert Einstein famous formula E is equal to mc square. According to this formula, amount of energy created is equal to amount of mass that is converted by multiplying the speed of light. Energy thus produced form the explosive power of the hydrogen bomb. Hydrogen bomb is based upon the fusion reaction of hydrogen to form the helium, producing the large amount of energy. Hydrogen bomb consists of the arrangement of nuclear fission in the center surrounded by mixture of deuterium and lithium isotope. Fission reaction provide the high temperature necessary to start the fusion. Core of the hydrogen bomb is a uranium or polonium fission bomb, and this fission bomb is surrounded by lithium hydride, which is compared to be heavy hydrogen. The fission give the heat and neutron, then the 6 lithium combined with the neutron give the 1H3 tritium with the release of a alpha particle and the release of amount of energy 4.78 MeV. Deuteron plus tritium give the 2He4 with the release of the neutron and the large amount of energy 17.6 MeV. When was this hydrogen bomb or thermonuclear bomb created? The US used the 2 atomic bomb in the World War II against the Japan, effectively forcing the country to surround it and ending the war. Then in 1952 and 1954, it was donated the hydrogen bomb in the Marshall Island. In 1954, US conducted further tests on the hydrogen bomb in the Bikini atoll in the Marshall Island. One of the bomb denoted as a part of series of tests called the Castle-Brabo. It produces the explosive believed to be up to the 1,000 times more powerful than that of atomic bomb that destroyed the Hiroshima. Bravo bomb yielded the 15 megaton, 50 million ton of the TNT, and was still the largest bomb that exploded by the US. Atomic Heritage Note, there is a written here, the largest ever hydrogen bomb known as the Tesser Bomba was donated by then Soviet Union in 1961 with yield of the 50 megaton. Then what is the difference between the hydrogen bomb and the atomic bomb? Atomic bomb uses either uranium or polonium and relies on fission, nuclear reaction in which the nucleus of an atom break into two pieces. Whereas to make the hydrogen bomb, one would still need the uranium or polonium as well as two other isotopes of the hydrogen called the deuterium and tritium. Hydrogen bomb rely on the fusion, the process of taking the two separate atoms and putting them together to form the third atom. In the fission process, the heavy nucleus split into the two or more light nuclei, and the fusion process, there are two lighter nuclei fuses together to form the heavy nucleus. And the fission condition of high temperature and pressure are not necessary, while in case of the fusion reaction, condition of extremely high temperature pressure are required for its occurrence, and so it should be carried out in the laboratory. Fission is a quick process, whereas the fusion in many steps there are finite time gap between the initial and final step. Okay. Then there is a energy generation in sun and star. Stellar energy. We come to the stellar energy. The sun radiate the energy at the rate of 4 into 10 raising power of 16 joule per second since the billion of year without any sign of cooling off. It has observed that chemical process like the burning of nuclear fission cannot occur in such large burst of radiation for the several billion of years. It has been found that hydrogen and helium constitute about the 90% of the mass of the sun and 10% of other elements. At very high temperature, which exists in the interior of the sun and star, proton fuses together to form the helium nucleus and liberating the huge amount of energy in the two processes, proton-proton cycle and carbon-nitrogen process. Hence, Bethe in 1939 suggested that source of stellar energy is a thermonuclear reaction. He proposed that thermonuclear reaction taking place in the sun and other star are by the two processes proton-proton cycle and carbon-nitrogen cycle. First we come to the proton-proton cycle. In it, thermonuclear reaction in which the direct collision of proton result in the formation of heavy nuclei. Proton-proton cycle, the two proton combine to form the deuterium 1H2 with release of the 1H0. And release of the energy 0.4 MeV, and this again the proton combine with the 1H2 deuterium result in the 2He3 with the release of energy of amount 5.5 MeV, and then this 2He3 combine with the 2He3 give the 2He4 helium and the 2 proton with release of energy 12.9 MeV. Hence here the 4 proton combine together to form the nucleus, helium nucleus, with liberation of total amount of energy 24.7 MeV. Then the energy generation and the source of energy source of the star, that is the carbon nitrogen cycle. It is thermonuclear reaction in which the carbon nuclei absorb a succession of the proton until they emit the alpha particle to become carbon nucleus. Once more it is repeated in the repeated cycle indefinitely. Carbon nitrogen cycle proceed as 6 carbon 12 combined with the proton resulting in the 7 nitrogen 13 with the gamma and release of the energy about 1.9 MeV. In the second step, 7 nitrogen 13 decays to the 6 carbon 13 with release of the positron and release of amount of energy approximately 2.2 MeV. In the third step, this 6 carbon 13 again combined with the proton resulting in the 7 nitrogen 14 with release of the gamma radiation and approximately 7.54 MeV of energy. In the fourth step, the 7 nitrogen 14 again combined with the proton 1H1 resulting in the 8 oxygen 15 with the release of gamma particle and approximately 7.35 MeV of energy. Then this 8 oxygen 15 decays to the 7 nitrogen 15 with release of the positron. Then 7 nitrogen 15 combined with the proton which result into the 6 carbon 12 plus helium nucleus and the gamma particle and a release of the energy, that is 4.96 MeV. In this reaction, whole reaction, we see that 1, 2, 3, 4 proton combine to form the resultant helium nucleus and the gamma rays and neutrino and liberate the total energy of about 26.7 MeV. Positron is also released here. Carbon is not consumed in this process. We see that carbon is not that started the reaction is not consumed in the reaction, but it acts as a catalyst in the formation of the heavy nuclei. It is found that carbon nitrogen cycle occur at the rather later stage of the life of star. Proton cycle takes place comparatively lower temperature, and carbon nitrogen cycle takes place at predominantly high temperature. In the interior of the sun, temperature is about 2 into 10⁻⁶ Kelvin, at which both the process are equally probable. A star having the temperature more than the sun obtain their energy from the carbon nitrogen cycle, and those at lower temperature from the proton cycle. That is all for today, and next day we will